All right, welcome back to the last session before the fantasy proof that we're about to go on. So the first talk of the session is on learning with errors, circular security and FG. The talk is by Daniele and the paper is by Daniele and Vinod. So thank you.
Okay, thanks for the introduction and thank you for having me here. And so in this talk, I'll be talking about circular security. That's the main topic. I'll start with a brief introduction and motivation to why we looked at this problem. And it is a problem that is well known, well recognized. It has been around for a while, but it has not received as much attention as it deserves. So in this work with Vinod Vankuthanathan, and I'll talk a little bit about what we did to try to push things a little bit forward in terms of our understanding of the problem. The talk will have more open questions than answers. I hope you will find it interesting. At the end, I will touch on some of these questions. So let's start from the basic definition of security. This is something that all cryptographers are familiar with. So in the standard definition of security for encryption against at least passive attacks, we have an adversary that is given a public key for an encryption scheme and selects two messages, M0 and M1, and is given the encryption of one of those two messages. And we said that an encryption scheme is secure if, given the encryption of one of those two messages, the adversary cannot tell which of the two messages was encrypted. Now, this is the standard notion of semantic security or indistinguishability under a chosen message attack already put forward by Goldwasser and Micali back in the early 80s. And it is a well-established notion. Now, something that is very important, fundamental to this notion, as originally introduced, is that these two messages cannot depend on the secret key. So they must be messages that are chosen by an adversary that knows the public key of the scheme, but does not have access to the secret key. And already in their paper, Goldwasser and Micali gave examples of schemes, artificially constructed schemes, non-natural schemes, where if the message depends on the secret key, or perhaps it is the secret key itself, then given an encryption of that message, the scheme can be completely broken. You can recover the secret key from an encryption of itself. Now, schemes that satisfies this additional security property that you can release encryptions of the secret key or some function of the secret key, these are called circular secure schemes. Now, you may wonder why we care about them. So there's a number of natural applications where this happen. One natural application is that of full disk encryption, where you have your secret key stored somewhere on your disk, and now you are encrypting your disk perhaps for the purpose of building a backup copy. And in this setting, you will naturally have an encryption of the secret key stored somewhere. Another classic setting where this appears is in the symbolic analysis of cryptographic protocols. In symbolic security analysis, typically one uses an inductive model of adversarial behavior. And encryption cycles are problematic if you want to interpret symbolic results in the standard cryptographic computational setting. And so there are some nice connections between encryption cycles or the absence of encryption cycles and how to link symbolic and computational security analysis. Anonymous credentials is another important application areas where encryption cycles are used as a feature. So in that setting, you want something that if there is a cycle, then perhaps you can break the scheme. Now, in this talk, I will be focusing on one more application of encryption cycles, which is that of fully homomorphic encryption. Now, fully homomorphic encryption by itself does not require encryption cycles, but it is a fundamental technique that is present in pretty much all the constructions of FAG. Now, FAG is something that you heard about earlier today. By now, is a pretty much standard problem in cryptography, so I'll be brief. So these are encryption schemes where you can perform computations on encrypted data. And from a technical point of view, we have essentially two classes of schemes, which are called leveled homomorphic encryption schemes and full homomorphic encryption schemes. And the first category, leveled schemes, they can be built from fairly standard lattice-based assumptions. Now, in a leveled encryption scheme, you need to specify the size of the computation that you are going to perform upfront during key generation time. So you can perform arbitrary computations, but you need to put a bound typically on the depth of the circuit that you want to evaluate homomorphically. And the deeper is the circuit, the bigger will be the key that you use to support the type of computation. Now, this works in a number of applications. There are a lot of things that you can do just using leveled homomorphic encryption schemes. But you may wonder, is there a way to build a scheme where you don't need to fix the size of the computation upfront? So those are the full homomorphic encryption schemes. It is something that is important from a practical point of view, because sometimes you don't have a bound on the size of the computation, or more generally, you want to keep your key small. So you want to be able to support big, long computations without having a key that is of a size proportional to the size of the computation. In fact, all practical homomorphic encryption schemes are of this type. And interestingly, even 15 years after the first FAG schemes were proposed with Craig Gentry's work in 2009, we still do not know how to build such schemes out of standard lattice assumptions. We say that we can build FAG out of lattices, but with a tweak. And the tweak is the fundamental bootstrapping technique introduced back then in 2009 by Craig in his breakthrough work, which is a method to transform a leveled homomorphic encryption scheme, which can be built now from standard lattice assumptions. You can turn it into a fully homomorphic one. And interestingly, there have been a lot of developments on FAG since then, but still to date, the only known method to build fully homomorphic encryption schemes is essentially going through this type of transformation. Now, it's a fine transformation, it's very elegant and interesting, but it requires circular security. So the transformation relies on releasing an encryption of the secret key, which is used during bootstrapping. Now, nothing in the definition of FAG says that you need circular security, but it is essentially the only known method that we have to build such schemes. Now, if you look at all the current schemes, BV, BGV, BFE, GSW, VM, and so on, so they all use this circular security assumption at some point to build arbitrary computations from a fixed key. And this has become a common assumption. It's something that is used without really questioning whether it is a good, bad, reasonable assumption. It has been used so many times that is considered kind of standard by now. And from a practical point of view, that seems okay, in the sense that no attacks were discovered to these schemes just because they were releasing a bootstrapping key consisting of an encryption of the secret key. However, there have been also very little cryptanalysis attempts. In some sense, there's been no cryptanalysis targeted to using those keys. And there is a reason for that, which I'm going to explain, that the circular security assumption that you find mentioned in most, if not all, FAG papers, is not really an assumption as it is now. It's not really defined formally anywhere. And something that I'm not considering in this talk is a different method to build FHE through indistinguishability obfuscation. I said that all schemes use bootstrapping and require circular security. So that's keeping IO aside, that's out of scope of this talk. Now, if we stick to the lattice-based construction, the reason the circular security is problematic is that it's more of a meta assumption than an assumption itself. So the assumption itself requires first to define a scheme. So you introduce an encryption scheme, and once you have the encryption scheme, you can ask, is the scheme secure if I give an encryption of the secret key to you? So each scheme, each FHE scheme basically gives a different circular security assumption. It's not a computational assumption in the traditional sense of the term, where you can state the assumption, people can study the assumption, and then you can use the assumption to build the cryptographic schemes. Here, the things are reversed. First, you build a scheme. After you build the encryption scheme, then you can state the assumption that allows to apply bootstrapping. Now, the fact that the assumption depends on the scheme makes it harder to specify cryptanalysis challenges. Every scheme is going to have its own assumption. And the reason I think the problem requires more attention is that similarly looking circular security assumptions were suggested in the setting of IO, indistinguishability obfuscation, and some of those were actually broken. So we think of this circular security assumption as something that is a pretty solid assumption, but it is really a problem that would benefit from more attention. Now, it's not a problem that we are going to solve in this talk, but we spent some time thinking about it, and what we did was primarily just some groundwork to make the problem easier to study and to attract some attention to this problem. Now, so the goal of our work was the following. We would like to get to a situation where there is just a single assumption or a small set of assumptions that can be studied in cryptanalysis. So people doing cryptanalysis, which are not that many of them, we heard that they are not well funded, we need more money for cryptanalysis. We also need fewer problems to focus those efforts. So we can identify a circular security assumption, which is specified at the level of a mathematical problem before defining first an encryption scheme. And then ideally you can transform 5 minutes left. Okay. And okay. So you can build many schemes out of the same assumption. So this idea would be useful for a number of reasons. For example, you could use it to generate challenges in the traditional sense and support reductions between different assumptions if you end up having more than one. And so in the paper, I'm not going to cover all those things. I will just give a single example in this talk. We describe a number of different assumptions. We show relations between them. For some of them, we can show equivalence to LWE. And we can also prove some results connecting different variants of the same assumption. For example, we can give a search to decision assumption for a circular LWE problem. Now, this is just a start. There is more work that is still left to be done than what we have done so far. So I want to describe what the assumption is. So take the LWE problem. You are given a random matrix A and then a vector of the form AS plus E. And the LWE problem is the problem of distinguishing this from a uniformly random input. Now, this is a very good problem. You can give challenges. You can study the hardness of solving this problem. And the assumption that we describe in the paper can be formulated as a version of LWE, given some public side information about the secret key. So you have a function pub of S, which is given as help. And the question is the LWE problem hard even given this type of side information? So let me skip this, which is a matrix generalization of the same assumption, and I will talk only about vectors in the rest of the talk. So there is a different method to formulate the same assumption. This is actually not in the paper, but I think is a nice way to put it. Consider a variant of the LWE problem where you have a function phi, and instead of being given AS plus E, you are given AS plus E plus phi of S, where phi is an arbitrary function, is a function that gives any vector modulo Q. Now, it's not something that you can decrypt. It's, even if you have, I mean, if you have S, you know what S is, of course, there is nothing to decrypt, but I'm not applying any form of error correction here. And so this is something that can be related to the previous description with a public function. But in the interest of time, let me just skip this relation and use it in the next slide. So there is a form of strong circular security LW assumption that could be formulated as follows. For any function phi, these two distributions are indistinguishable. Now, this is a very strong assumption, but because I'm requiring this for any function phi, but at the same time, I don't know any way to attack it. A similar, even stronger assumption was suggested in different contexts, in the context of Fiat-Shamir protocols. And there is one aspect for which this assumption is a bit unsatisfactory. From one hand, you could tell to the cryptanalyst, oh, you can pick any phi that you want. If you find one for which you can break the problem, great. So this problem is broken. But so this is an interesting approach to the cryptanalysis problem. But you cannot give challenges. In order to release a challenge, which is what cryptanalysts want, you need to fix this function phi. So you cannot really let the cryptanalyst choose it first. So in order to move forward with this problem, one could consider what specific functions phi are of interest in the construction of FAG schemes. And in the paper, we describe one such function. It is described using lattice gadgets. And so if you're familiar with gadgets, you can think of the power of two gadgets. So given a value x, you consider also x to x for x multiplied by power of 2. And using these gadgets, you can encode arbitrary values modulo Q in a way that is redundant and allows you to correct errors. Now, so using this gadget, you can define an LWE encryption that encrypts messages modulo Q, not just the modulo P for some smaller modulus. And now you can use this function to produce a public information about the S, which is a gadget LWE encryption of the bit decomposition of S, or more generally is a quadratic function of the bit decomposition of S. Now, this is something you find in some of the previous schemes, and it is enough pretty trivially to prove that under this circular security assumption, some schemes are indeed secure, because that's exactly what is given as an evaluation key. But interestingly, we were able to prove the security of also of other schemes with at face value they look different from it. So something else that we do, which is non-trivial, is to give a search to decision reduction for this assumption, which is not just the standard LWE search to decision, because you have an encryption of S under S. And in order to do this search to decision problem, you need to change not only the encryption key, but also the encrypted message inside. Okay, so let me, so this was a sketch of how the reduction work. All the reductions in the paper, they are very, very simple, but they suggest that there is work that could be done. So let me conclude with the open problems. So what we do in this paper is something that is, at this point, is just theoretical results, are not reductions which are useful from a concrete point of view. In the process of mapping one problem to another or different types of assumptions, you lose quite a bit in terms of error size. So it's not something that right now can be applied to the schemes we use in practice. Also, the paper focuses on schemes based on the standard LWE problem for arbitrary lattices. It doesn't consider the ring LWE setting, which of course is more interesting in practice. But hopefully, yeah, somebody will pick this from here, look at the problem and prove some great results on this problem. Okay, thank you.
While the next speaker sets up any questions for Daniel. So Daniel, maybe I can start with one question. The next speaker, Lauren, you can come up. So do you think there could be a complete class of the fee function that we described here, such that that fee class is basically complete for any circular LWE, the most general definition of circular LWE?
So in some sense, that's the idea behind our proofs. And the idea is the intuition is easily explained. If you have some fee, which is enough to build an FHE scheme, then you can use the FHE scheme to change that function into something else. You can do computation on this public information and turn it into another piece of information. So in some sense, the circular security assumption that is needed for LWE is complete in this sense.
That's great. So let's thank Daniel again.
Those slides are slides.
Oh, sorry, did you choose share the screen? Why is share this? Since more is share the slides. Someone is share this slides. Please share screen. No. Now you stop share. Stop.
Okay.
Yeah. So I share got some wrong information. Yeah. Share the screen. The first one. Yeah. Someone share the slides. So that's the one. The recording kind of save the slides.
Slides. Okay.
Well, they should be able to.
And is it recording already?
You can
Still cannot.
and the last one, you the previous one. So ISR, they can.
Is this recording?
Yes,
It's recording.
You can ISR.
Perfect. Okay, great.
All right, so some technical glitches solved, but it's my pleasure to introduce Lauren, who's going to tell us about chosen ciphertext secured receiver encryption, the standard model based on post-quantum assumptions. And this is a joint work with the Vasilij, Sarai, Roland, Maximilian, and Jon. So just go ahead, Roland.
Thank you. Okay, it works actually. So we tried to get along this title possible, but actually somebody else submitted a paper which had an even longer title. But I'm still gonna just go quickly into what's written there. So basically, parts in the title. The first one is the chosen ciphertext security, which I guess most of you know. It's basically like an extension of the indistinguishability under the chosen plaintext attack that we just heard before, where you also get an decryption oracle as the adversary. We have the standard model, so we're not using any random oracle model or generic group model or anything else. We're just using plain cryptographic assumptions. We're based on post-quantum assumptions. Well, at least we think we are. Depends on the LWE paper. And we have dual receiver encryption, which I guess not many of you know. So this is what I'm going to explain first. And also, when we talk about dual receiver encryption, we will have to talk about the chosen ciphertext security really quick because the definition is a bit different, but not by that much. So what is dual receiver encryption? Basically, what we want in dual receiver encryption is we want to encrypt a message to two different receivers. And if we would not only encrypt a message to two recipients, but to more, then we would get broadcast encryption, which I guess a bit more of you might have heard about. And so basically the definition is just the usual three tuples. We have a generating algorithm, which takes a security parameter and outputs one public secret key pair. We have the encryption algorithm, which takes two independent public keys and the message and outputs the ciphertext. And then we have the decryption algorithm, which takes one secret key in addition to the two public keys and outputs the message MI. Just a quick remark, we used R and S because most of the time in the applications of dual receiver encryption, we actually encrypt the message to the receiver and to the sender. So this is why R and S are used. A naive implementation of a dual receiver encryption scheme could be we take any public key encryption scheme. And well, for our dual receiver encryption scheme, we just reuse the generating algorithm. So we generate just the same public and secret key pairs. And to encrypt the message, we just encrypt the message independently. Well, first with the first public key and then with the second public key, and then just concatenate the messages or the ciphertext. And we call this CR and CS just to be able to decrypt later on. So when we want to decrypt such a ciphertext, well, we just take one of the secret keys and then we use the public key encryption or decryption algorithm to decrypt the message to what we wanted to have. So the question now is this DRE scheme? And the answer is yes, actually it is, at least so far, but it's also not very useful because what we actually want from the dual receiver encryption scheme is we want that both parties get the same message. Otherwise, it's just not really useful. And we want this to be true even for malicious ciphertext. And in our case, malicious ciphertext means that an adversary gets both secret keys in addition to the public keys, and then can create a ciphertext which he tries to make sure that that it decrypts to two different messages. This property is called soundness. So if every ciphertext decrypts to the same message under both secret keys, then this is called soundness. And the formal definition would be true again, but I'm not talking about it here. Okay, I said before that we have to talk quickly about the CCA2 security. Basically, it's the same security as in the public key encryption game, with the difference that the adversary now obviously gets two public keys, so he can encrypt messages. And the decryption oracle is also slightly different in that instead of only sending a ciphertext to the decryption oracle, and now we actually have to say which of the two parties we want the message to be decrypted to. Actually, if we have a sound dual receiver encryption scheme, this is just the PKE CCA game because, well, it doesn't matter which of the two parties the ciphertext gets decrypted to. Okay, what are the applications of sound dual receiver encryption schemes? First one would be plain text awareness via key registration, in which we just want to make sure that every sender of a ciphertext also knows the message that is in the ciphertext hidden. And we want this, for example, for the dual FER model, which is a model that we use for proving for automated theorem provers. Another application would be a key exchange with incriminating abort, which is basically a key exchange where we want deniability in the case of a successful finish, but we accept that it will not have deniability in case of one party collaborating with the adversary while the key exchange is in place. What we also can get with dual receiver encryption is public key encryption with non-interactive opening. And there is some more stuff, but yeah, just for quick applications. So before we get to our contributions, first some related work. So what was there before? Before we already had sound DRE schemes which were based on post-quantum assumptions, but those were only in CPA secure. We also had sound CCA2 secure DRE schemes, but those were not based on post-quantum assumptions. And we also had post-quantum CCA secure DRE schemes based on post-quantum assumptions, but those were not sound. So basically nobody else, I don't know if they never thought of it or never made it, but there were no sound CCA secure DRE schemes based on post-quantum assumptions. And actually our first contribution was to show this. We looked at all known post-quantum assumption-based CCA2 secure DRE schemes and showed that they didn't satisfy the soundness property just by constructing malicious ciphertext. And after that, because it's not that fun to just destroy stuff, we also wanted to construct two efficient post-quantum secure CCAs, post-quantum based CCA secure DRE schemes with the soundness property. One of them is based on LWE, and the other one is based on LPN. For those of you who don't know LPN, that is the learning parity with noise problem, which is just a code-based assumption. And we really used only the low noise LPN assumption. This is also the first DRE scheme ever based on LPN. And it's inspired by an LPN-based PKE scheme by Kitz et al. From 2014, which is, as far as we know, is still the most efficient PKE scheme based on LPN assumption. CCA2 secure PKE scheme. Both of our schemes use the hybrid encryption paradigm, and so they share a lot of code. But I'm not going to show you everything because it's quite a big construction. But we're going to look at some of those parts. So what is the hybrid encryption paradigm? If you look at our encryption algorithm, you will see those four parts. So basically what we do is we draw our secret, just a random secret, and then we use the secret to derive the data key and the MAC key. And then the real encryption takes place in the symmetric space, right? So instead of just encrypting the message with the asymmetric encryption scheme, we encrypt the key for the asymmetric and for the symmetric encryption scheme, and then encrypt the message symmetrically. The reason why we do this is just because it's faster. So yeah. Another thing I want to point out is in the decryption algorithm, we have those 4 parts. So basically, every time we do a CCA secure LPN or LWE scheme, we have to do some consistency checks to make sure that the error is not too large and that we are able to decrypt to the correct message. And the good thing is that we are able to do this with only the public keys. So we don't need the secret keys for this consistency check. And in our case, this means that we get the soundness check nearly for free. So the first part is always just to make sure that actually the message we receive is the correct message. And the other check is then to make sure that the other person or the other party gets the same message as we do. Another thing I want to have a look at is the ciphertext itself. So the ciphertext, or the asymmetric part of the ciphertext, consists of 2 parts, C0 and C1, and they're kind of like doubled because we have to encrypt something to party R and party S. But actually, this is very low overhead compared to the LPN PKE of Kitz et al. Because they also needed 3 vectors and we only need 4 vectors instead of 6 vectors. So the overhead is pretty low. And actually, our public key sizes got reduced as well. So we are comparable to the PKE, even though we encrypt to 2 different parties. We do this because, well, our CR and CS naturally act as a double trapdoor. So every time we want to make a CCA secure PKE scheme, we need some kind of trapdoor to be able to extract a secret. And in our case, or even in the case of Kitz et al., they needed a double trapdoor to allow the simulation of the decryption oracle. So what is CR and CS? Well, CR is everything that's encrypted for party R, and CS is everything that's encrypted to party S. And why do we need this double trapdoor? Well, basically, if you would have a look at the public key, you would notice that the public key consists of 2 matrices, A and then A1. And A1 is just A times R, where R is the secret key. And for the proof, we actually need to replace this public key, the A1, with A times R plus X, or X is a known matrix. So basically, the adversary or an adversary would try to distinguish between the public key A1 equals A times R and A times R plus X. And the question is, can the distinguisher do this? And the answer is sadly, yes, it can. Because we're in the setting of low noise LPN, this is possible. And so we will have to think about another way to do this indistinguishability game. So what would be nice is if instead of A times R, we would have a uniformly random matrix here. So if a distinguisher has to distinguish between a uniformly random matrix and the uniformly random matrix plus an extra matrix, well, this is not possible because basically it's the one-time head, right? So yeah, the distinguisher couldn't do anything here. And this is basically what allows us to do this replacement. So we first exchange the A times R with a matrix, then we add our matrix X to this public key, and then we change our uniformly random matrix back. And the first and the last step are done by the LPN assumption, or actually the Knapsack LPN assumption, which is just a dual version. And yeah, the second one I just said before, this is basically a one-time pad. So now everything's well, not really, because in all this time we have to be able to decrypt, right? So if an adversary actually uses this public key to encrypt the message, we as a decryption oracle would have to be able to decrypt the message. And this is possible in the first and the last step because the X is chosen in a way that allows us to still decrypt the message. But it's not possible when we replace the public key with the random matrix, because then we just lose our trapdoor. So in this case, we cannot decrypt anymore. Okay, so what do? Well, we have some dual receiver encryption scheme. So even if the adversary encrypts the correct message and then asks for the message that would be decrypted using CR, actually we can just use CS. And this is the basic trick, okay? So this is the double trapdoor. Instead of only having one encryption scheme or only one encryption part, we can just use the one for for the party S. And after we did this adaptation, then we can just do the same thing for the other public key, so for A1S, and finally end up with everything that we can then reduce to LPN. Okay, I said before that we have another contribution. So we also made a scheme based on LWE, which is actually pretty similar. So the construction is similar, the soundness check works the same way, but it's even easier to prove because A1 is statistically indistinguishable from randomness. So we don't need to do this double trapdoor kind of way, which makes it a lot easier. The resulting scheme has bigger ciphertext, but smaller keys and a lot smaller keys. So it's kind of like, yeah, it's a trade-off. And this is basically what we did. So we showed first that the post-quantum CCA secure dual receiver schemes are not sound. Then we fixed this by just creating two schemes, which satisfy all three properties. And everything that we use actually known primitives, like the trapdoor already got implemented. So it's pretty easy to do a proof of concept implementation. In fact, this is just being done at KIT by a student. And there's also a lot of room for improvements, like using rigged up LWE instead of the normal LWE. And more importantly, in my opinion, is you could just save or reduce the size of the public keys and the LPN version by just using some compression techniques because it's low noise. And with that, I'm already finished, a bit ahead of time, but I think it's good because we need to go to Frankfurt later on. So I open the floor for any questions.
So,
Okay, so basically what you want to do is like that's public key encryption with non-interactive opening. Basically what you want to do is, where is it here? You want to encrypt the message and be able to let the receiver open the message. So actually prove that one of the encryption actually encrypts the message that we want to show without compromising the security of the scheme itself. So basically, yeah, that's what we do there. And in the dual receiver case, it's pretty easy to do this one time. If you want to do it multiple times, you have to work a bit harder. Sorry, I didn't understand you.
So your work, you emphasize
Yes.
understanding.
Yes.
So I'm aware of a paper.
And it's actually a good question. So the other schemes were, so the ones which weren't sound didn't use any other model either. So they were all in standard model as well. But there actually is a CPA secure, funnily enough, which uses another model. But basically, this is not the new thing. The new thing is that it's sound and post-quantum secure.
Great. Any other questions? So maybe I have a quick question. Would Naurion paradigm sound?
With what?
Naurion paradigm
What's that?
that converts a CPA scheme into a CCA scheme generically by using a NIZC. So NIZCs are in the CRS model. I'm not assuming the random oracle based ones. You take two CCA schemes, tie them together using NIZCs, and that way I think it technically that would give you post-quantum dual receiver.
Probably it would work.
Okay, it might not be as efficient, that I agree.
Might probably be a lot less efficient.
Yeah.
Correct. But
Theoretically,
theoretically, it should work.
so let's just thank Lauren again.
This one. Let me check with my share.
So the last one of this section is on more efficient public key cryptography with leakage and tamper resilience. And the talk is given by Shuai, and the paper is by Shuai, Shingli, and Tom.
Thanks for the introduction. Good afternoon. I'm Shuai Han, and I'm going to talk about more efficient public key cryptography with leakage and temporal resilience. This is drawn to work with Shengli Liu and Dao Wu. Traditionally, when analyzing and proving security of cryptographic schemes, we usually assume that the adversary can have only black box access to the devices. However, in reality, the adversary may go far beyond the black box access. In particular, through various side-channel attacks like power analysis, timing, measurements, etc., the adversary may obtain partial information about the secret key. Such attacks are usually passive and called the key leakage attacks. On the other hand, the adversary may also launch active attacks like the fault injection, memory tampering attacks, etc., from which the adversary may force the device to operate under a different but related key. For example, here the adversary may force a decryption device to decrypt the ciphertext under a modified key TSK. So it is important to ask how to achieve security resilience to both the leakage and the tampering attacks. To deal with this threat, up to now there are several security models. The first one is called the CTO model, proposed by Kage et al. And this model considers continued tampering and leakage attacks, and it provides a very strong security guarantee. But it needs additional mechanisms like key updating or self-destruct of the devices. And Kage et al. And Fujisaki Kusagawa proposed a signature scheme and a CCA secure public key encryption scheme, respectively, in this model. And their signature contains more than and their signature contains more than 20 group elements, and their ciphertext contain more than 8 group elements. And their constructions rely on heavy tools like the true simulation extractable NISIC or one-time loss filter. The second security model is called the BLT model, proposed by Damgard et al., and it considers bounded leakage and temporary attacks. Here bounded means that it can tolerate a bounded amount of leakage and a bounded number of temporary queries. The benefit of this model is that it's no longer requiring additional mechanisms. Fionio and Venturi proved that the signature scheme proposed by Dodis and the PKE scheme proposed by Qing and Liu actually are secure in this model. And however, their signature contains more than 34 group elements and their ciphertext contain more than 19 group elements. Their schemes also rely on the TSC NISIC or one-time loss filter. The third model is due to Sun et al. And called the SLTR model. It considers strong leakage and temporary resilience. It also considers a bounded amount of leakage. However, as for temporary, it allows an unbounded number of temporary queries, while the temporary functions should be specific functions like the affine functions. And it also does not need any additional mechanisms. Their work focuses on PKE, and they use TSC NISIC to build a CCA secure PKE in this model, whose ciphertext contain more than 20 group elements. The fourth model is proposed by Chakrabarty and Reagan, and they extend the BLT model to post-challenge BLT model. They also need the additional mechanisms like the split state of the secrets, and they focus on PKE, and they use the TSC NISIC to construct a CCA secure PKE in this model, which contains 20 group elements in their ciphertext. So up to now, all the existing schemes resilient to both leakage and tampering attacks have large signatures and ciphertexts. The main reason might be that they all resort to heavy tools like TSC NISIC or one-time loss filter in their constructions. So it is natural to ask how to achieve security resilience to both the leakage and tampering attacks in a more efficient way, and in particular without using TSC NISIC or other heavy tools. And in this work, we answer this question in the affirmative by proposing very efficient signature and CCA-PKE schemes. In particular, our signature scheme contains only 4 group elements in its signatures, which is about 5 to 8 times shorter than the existing schemes. And our CCA-PKE schemes contains only 6 group elements in its ciphertext, which is about 1.3 to 3.3 times shorter. And to achieve good efficiency, we propose our schemes by direct constructions over asymmetric pairing groups and without using TSE NESIC. And we prove their security based on the standard MDDH assumptions in the standard model. For leakage resilience, our signature scheme can tolerate a leakage rate of 1/4 minus small 1, and our CCA-PKE can tolerate leakage rates of 1/3 minus small 1. As for temporary resilience, both of the schemes can tolerate affine functions and the temporary functions, the same as the existing schemes in this model. So next, I will show the security model we considered in this work, namely the SLTR security model, and then we show how we propose our efficient signature and CCA-PKE schemes. For PKE, we adopt the SLTR model proposed by Sun et al. And in this model, the adversary can make 2 kinds of queries adaptively. Through leakage queries, the adversary can obtain bounded partial information LSK about the secret key. And through decryption queries under tempered keys, the adversary can obtain decryptions of the ciphertext under the tempered secret keys TSK. And this model makes only minimal restriction on the adversary's post-challenge decryption queries under tempered keys. And for signature schemes, we propose a new SLTR model as a counterpart to the SLTR model for PKE. And in our model, the adversary can also make 2 kinds of queries, leakage queries and signing queries under tempered keys. Through signing queries, the adversary can obtain signatures signed under the tempered secret key, TSK. And finally, the adversary outputs a pair of message M star and the signature sigma star as its forgery. The adversary wins if the forgery passes the verification and it is fresh. And here we only make a minimal restriction on the winning condition. More precisely, during the signing queries, we use a set QID to collect the message signature M sigma pair signed under the original keys, and we require the forgery M star sigma star outputs by the adversary not in this set. And this also reflects the strong existential unforgeability of the signatures, which even guarantee that the adversary cannot forge a signature for an already signed message. Next, we show how we construct our signature scheme. Our signature is constructed over pairing groups, and here we use brackets to denote the group elements. Roughly speaking, the public parameter PP is related to K0 and K1, and the secret key and verification key are related to the matrix key, the matrix K. And to sign a message, we first sample a vector C from the span of U, and then we use the secret key K to compute K times C, and then use the K0 U, K1 U contained in the public parameter to compute the second term. And here tau is a tang computed from the message. Then we add these 2 terms together to get D, and the signature contains C and D. To verify a signature, we first ensure that the vector C is non-zero, and then we check the correctness of D with the help of the pairing operation. Here, the secret key contains is a matrix K. So the leakage and tampering attacks will only affect the first component, and but not the second one. Here we can pass our scheme as 2 components. The first component is related to the matrix K, and the second is related to K0 and K1. And during the generation of D, we carefully integrate these 2 components together by adding them together to to make the signature shorter. Here we show the first component more clearly. And here the verification of D is actually equivalent to the check of whether D equals K times C under the MDDH assumption. And for the first component, we observe that it actually satisfies a very useful property that given only the verification key, it is hard for the adversary to forge a signature to pass the verification. Namely, C is non-zero, but D equals K times C. This is because that condition on the verification key, there is some entropy left in the secret key, which makes the K times C hard to guess. And this argument holds even if the adversary can obtain additional leakage about the secret key. So consequently, the first component achieves security against no message attacks under key leakages, meaning when there is no signing queries. And here we show the second component more clearly. One may notice that this component is essentially the one-time simulation soundness proposed by Qt and we. But here the property of one-time simulation soundness is insufficient for our purpose because here the adversary can ask multiple signing queries and obtain multiple signatures, which contains multiple NISIC proofs. Instead, we resort to another property as observed by Qt and we that this component behaves as a randomized PRF on the tank top. So it can mask the first component during the generation of D and hide crucial information about the secret key. A subtle problem is that to use this property, we need to ensure that the tag involved in the forgery is different from the tags involved in the signing queries. And we prove this by a careful analysis and resort to our concrete algebraic construction. And finally, we can show that the signing oracles under tempered keys are in fact useless to the adversary. Overall, the first component achieves security against no message attacks under key leakages, and the second component can mask the first component during the signing queries under tempered keys. And putting them together, we finally obtain the SLTR security of our signature. And finally, we show our CC-PKE construction. Our PKE shares a similar design with our signature scheme, and it can also be passed as two components. And the leakage and tampering attacks will only affect the first component, but not the second one. And in the encryption algorithm, we use the first component to mask the message, while use the second component to prove the well-formedness of the ciphertext. And roughly speaking, we can show the first component can achieve CPA security under key leakages. And we can show the second component can reject decryption queries under tempered keys. And putting them together, we can get the SLTR-CC security for our PKE, which can resilient to both leakages and the tampering attacks. And this is the end of this talk. Thanks for your listening.
Taking the leakage class to be, I think it was a find functions in this case and all the prior words and extended to more general class leakages.
Here our focus is to improve the efficiency, so we resort to we use the direct constructions. I think it's interesting to maybe consider a generic construction for a larger function sets. Yes, thank you.
If there are no more questions, I think we are all good to head for the cruise. Okay, thanks. Let's just thank all the speakers in the session.
Yeah, rule number 6.